Okay, good afternoon. Okay, so first of all, thank you for working with me. And then, how was the exam? I mean, I think I mentioned what. Okay, variety of reaction.
I don't think I did as good as last time, but I did good last time, so who knows?
Yeah, still,
It was so time constrained.
Oh, really? Yeah.
I don't know how many people. I knew one person walked out of the room.
Oh, really? How was time? So.
Didn't finish or were rushed to finish, so just completely overwhelmed on that.
I see, I see. So no time to review or?
No, if you didn't know the tricks of the questions, if you didn't know what the questions were asking exactly, there was no time to figure it out without Yeah.
I see, I see, I see.
There was no second chances. Like if you didn't know it, you just.
Okay, okay. Yeah, I mean, I understand your comment. Yeah, I see, I see. Any other comment? I'm just like, this is free discussion. You can say anything you want, right? Because you are not recorded, right? My side, right? I don't watch video, but, so don't worry about it, And yeah, it's kind of long, lengthy, yeah. Yeah. I have not seen, I have not, received any. Yeah, it's lengthy, yeah. Okay. Okay, so lengthy, okay, I understand, okay. Any other comment? Just basically lengthy, it's not like, like I'm trying to trick, but it's lengthy, I get it, yeah. So let's wait, yeah. No, okay. I mean, because I want to hear, I'm not going, because of that, and I'm not going to do anything. No. I just want to hear that. Then first, I'm going to wait for TA to grade, because I think TA is grading still homework 4, Hi? It's already graded? Okay. So then he's going to start, because before I left, I talked to him, and then, okay, kind of, he said at that time he was doing homework 3, and then, and then homework 4. Okay, then hopefully, when I talked to him before, I left, and then he said he may start maybe like this week, like Wednesday, he will start grading. Or if already homework 4 was, graded, maybe he will. But after that, I will review as usual, and then if I see some questions of how you behaved, like also I compare on-campus students and edge off-campus students. Like last time I see some trend differences, and then this time I will see on-campus student and off-campus student, then differences, and then I have to decide I have to grade separately or like that, right? Just where the fairness I have to just to see. So then we can maybe bring up one more time discussion based on the graded exam. And then, if it's, I think everybody did well, even though, but then depends on that. And then, like makeup exam or something, extra assignment or something like that. But I just don't want, I want to tell one thing. I usually, and then almost never, I don't curve. So if I see some issue, okay, lengthy students could not show, and then somehow another extra assignment or something, I will just try to make sure students understand the material. That's kind of fundamentals, I always do. But let's wait, Yeah. Oh, okay. You can. Anybody can talk to me, anything you want. Again, I'm not gonna do anything, retaliation, anything, nothing, This is, we both, we want to make sure we are on the same page. We are learning. Yes.
I just don't how time constrained we didn't have the ability to show that we understood it because we were so pressured to just get through the
I see. Okay.
You didn't know exactly what you were doing, and you had to think about it. Like you lost so much time. You had to, I ended up having to give up a question basically because I didn't know. And I know some other people were struggling with that.
I think the material, all the exam was really fair. I understood it. I just was so rushed that I was kind of freaking out.
I see. Okay. First of all, so sorry. So sorry. But the amount I put is, actually same or a little bit one question less than last year. So I thought it was okay based on that, but it doesn't mean, right? It doesn't mean you are good or bad or anything, right? Because how I deliver material, right? And because I think I'm doing same thing, but maybe different, right? So it's not just your side. It's my side too. That's why I'm kind of spending time to get feedback and so then how we go from here. Because the goal is, not just, giving you A, B, C, D. If I want to give just, okay, everybody is I want to make you happy, I can give everybody A, right? Does it help your education? Probably not, right? So then where is the fair, part, right? And then, what?
It helps the stress.
Oh, sure. I get it, but right? So then what needs to be done? And then also as a graduate level, this is a graduate level course. What I expect for the graduate level, I need to make sure, right? So but I know some undergraduate students are here, but just have to, keep. So that's, want to think about. Once, I see the, graded exam, yeah.
The one question I thought was a little odd was the lead question, because it was like, it was kind of out of left field, I guess.
Which one?
That you can't cold roll lead because its recrystallization temperature is under room temperature.
Yeah, that's in the homework, exactly same question, right? Yeah. And we talked about it. Yes, and then we talked about it in class. Yeah. So, but anyway, yeah. Yeah. So, just to, but you forgot. It happens. It's not, Yeah, right? Because you have so many things, so it just happens. That's it. But yeah. But anyway, I just want to hear because I wasn't here. I was in a conference. Conference is great, but now no more trip. I'm here, and I'm done. So then I want to be with you, and then let's, study together till the end, So exam 2 is done, right? Unless we have something. So for final exam, the material should be, included from today's lecture. It's not cumulative. So I'm not saying you can forget. I don't want you to forget, but but you know where to look at, right? So, but anyway, I just want to tell you, this is stress relieving, right? So you know exactly, So from today's material until the end, I believe it's going to be December 4th, So, okay. So then today, I just, told before and also updated the schedule. So we do plastic, and then so like the way I planned at the beginning. So quickly, we do plastic. And then this semester, because of hurricane, you need to kind of press. I don't know how much I can, cover. I'm trying. Okay, so today is, October, already end of October, 28, chapter 6. So that's processing of polymers. So we already talked about the polymer, what kind of polymer we have, like thermoplastic, thermoset, I think at the beginning we did. But we can just quickly review because it's a long time ago, right? I mean, yesterday level, but long time ago. So then more focusing, like blow molding. I mean, I don't know what injection molding. You heard at least, these terms, right? Like a pet bottle, you drink, right? And then, that's what kind of process? Blow molding, right? So something like that. So you use, because a lot of material, made of plastic, a lot of products made of plastic you use, But this time is good, kind of, reviewing time what, oh, okay, I'm using this, but how it's made. Then some water bottle, metal one, that's not blow molding, So that's a different process, okay? So then, we are already, just jump into just, summary of some, selected material, So selected materials. The textbook said selected polymers, but it's the same things. I just so thermoplastics, thermoset, and then maybe one more thing, rubber, which is elastomers. So that's the three kind of selected, polymers. Right. So the major difference between thermoplastics and and the thermoset. So thermoplastic, it's recyclable, right? So you can heat up, and then you can, kind of melt, or, rubbery kind of things, and then you can cool down. They can, kind of cure, and then, you can reshape or reprocess, and then, you can make, some parts. So which means this thermoplastic, so they can be only rigid, below the glass, transition temperature. So we put a TG just for now, right? So then, like PET bottle I already mentioned, right? So like polyethylene or even polypropylene, maybe PVC, you know these, right? At least like PVC and polystyrene. So that's kind of the example, just to, and then polypropylene. Acrylic is also, the group, same group, polypropylene. PP, maybe just PVC. PVC is PVC, polyvinyl chloride, right? PVC, and so something like that, Maybe I mentioned polystyrene. I can do that too. Styrene. PS. Okay. So then again, I said, this is good thing is, so these are example, right? So this is okay, recyclable, So that this below, below, TG is from here, TG. So, I've already mentioned, but just, hard, just simple, brittle, and glassy. And then above, TG, that's viscoelastic, right? So which means you heat up, so this polymer, so you heat, right? So you heat, then this polymer becomes softened, right? And then, after that, you cool, right? And then this, stiffen, right? So that's the things. How about the thermoset, So thermosets, yes, so you can kind of melt for kind of, shaping, right? So this, so first, step 1, okay? So same thing, melted. Shaping, and then cure, you will cure, cured, sorry, not for, cured 2. Harden, right? So that's like harden, that's, people a lot of say that it's a cross-linking, right? You heard, right? Polymer, cross-linking, and then, it's really rigid, Okay. So once it's cross-linking, you cannot be melted. Okay. Or, yeah. So once you melted, right? Because this cannot be recyclable, right? It cannot, right? So in this case, so then you heat, right? And then, compared to previously, you heat, make it kind of, stiffer because of chemical, like epoxy. Have you ever used epoxy? Epoxy A and B, right? You mix, right? And then as soon as you start mixing, the heat is generated, right? Because they are chemically reacting, right? So that heat is going to actually make it stiffer. And then, kind of curing, like cooling down, but it's a curing, but it's not going to do more and more. So previously means like thermoplastic, you heat up, right? And then that's going to be more soft inside, right? So that's the two fundamental differences. Okay? So so can I change page? So then it's continuation, So in this case, thermoset and, heat, right? So that's to stiffen, right? And then cool, right? And then, then cool down. So it's like still stiff already, It's just cool, or this is like even, yeah, it's like a curing. That's no change. I mean, it's not going to be softened. So that's just basically I will go like that. That's cool down, So that's a major difference. And then this, cool down, or even this is, heat up. So, it's like a, so that's curing, right? So then this, stiffen or even harder, make it harder, right? So this, curing. So that curing part is like even chemically, I just epoxy-wise chemical, right? But also radiation, that's also sometimes light, right? Radiation, that's also, curing, but kind of heating inside, and then going to make, this polymer is going to be, soft, not stiffen, and then just back to room temperature, you just have to cool down. So this action can be done by chemically induced cross linkage. Okay. So then there's some example like I draw up, before, and then same thing, just epoxy, and then maybe resin. So if you have some hobby, and then some people use resin, like mix A and B, like a transparent, and then make some kind of tabletop or some kind of jewelry or some that's like resin. That's another probably you see. Of course there are other like polymer too. It's listed in the textbook, but these are more like probably you see or you already used or you did some experience or experiments too. Epoxies may be major. So anyway, these. So the blow molding we talked, right? PET bottle. So PET bottle is, of course, recyclable, right? So when you throw away, you put into recycle bin or something. So because you can heat up, so that thermoplastic, that's good for blow molding, right? Or even injection molding, right? But thermoset, it has to be flowable, right? If you want to produce something, so they can, but not good for. It's very difficult to use, thermoset material for blow molding. So now you see that it's not like memorizing, So that's maybe the, like you can see how we can differentiate when you use. Okay. I will list later, when we got, this is still kind of review of the polymer. Okay. So then, last one, the third one, that's going to be elastomer, right? So usually we don't say elastomer, we say like rubber, right? Right. So that's not as heavily cross-linked, like elastic, right? Because if it's heavily cross-linked, it's so rigid. Makes sense? So then, that's why, it's kind of expandable or deformable, So, okay. so this cross linkage of this. It's okay. That's why this you can remain or retain high degree of elasticity. Right? So also this cannot be reverted to the original state, because first you have to mix and you have to make like a cure, right? So it's not like a recyclable things. It's not, And then this, maybe this is amorphous. So amorphous polymer does not have a specific, melting point, but they can be kind of, change the mechanical property, the small range of certain temperature. Because rubber, it's, natural rubber, synthetic rubber, right? And then, it depends, like a tire, right? Driving tire. So your tire and racing car, Formula 1 tire, it's really different characteristics, right? So then depends on what you want to kind of use as a ingredients, and then mixing rate is going to change. This, like I said, even glass transition temperature, and also how you are going to manage a mechanical property. So the so that's the key point. And then again, so natural natural rubber or either synthetic. Rubber. So natural rubber, just for your information, glass transition temperature, negative 70 degrees Celsius. So we are, kind of, like room temperature, right? We are beyond, above negative 70 degrees Celsius, right? So that's why it's going to be good, right? But if you freeze, this, rubber, even natural, and then really lower temperature, below negative 70 degrees Celsius, rubber is going to be very, hard, brittle, and then they don't do like expandable or something, So that's why, rubber is always in our kind of this environment. It's going to be, like very elastic. So synthetic one, of course, it has to have some, relationship with, this transition, glass transition temperature. So usually synthetic rubber, so styrene and, butadiene rubber. Okay. So then usually SBR. So it's like a copolymer. So sometimes I just put the plus, or sometimes people put just dash or something, But the key is this styrene transition and glass transition temperature plus 100 degrees Celsius. But this butadiene side, that's negative 85 degrees Celsius. So it depends on the mixing ratio. Then you can control as a product, glass transition temperature, and then also mechanical property, right? So the tire, again, I don't know if you had a chance to see the racing car. They wear a lot, right? Of course, the speed is different. Okay, our driving, 40 miles or 60 miles per hour. Formula 1, what's the speed, And then braking, right? It's a totally different world. But it means they have to withstand, right? Their tire, withstand, that kind of severe high temperature, and also, like sliding. So they're totally different. But it's still rubber. Like, the color is black, right? And so anyway, that's how, they manage, So this, ratio is the key to control, their performance, the ratio, product. Right? Yeah. Again, TG, they are controlling. So I think, that's kind of the review, okay, 3 kinds, major things, and then, okay, why they behave like what you see, right? So let's talk about the processing, because now we know how this, what kind, right? So then process-wise, chapter, section 6.4, okay. So now, there are like, several, things included in the textbook. Then I'm just going to list, and then let's talk, And then we have, I want to also share some video, So, but just the list first, So extrusion. Extrusion is extrusion, okay? I think, you know the metal or even candy, some like a rubbery candy. I don't eat that, but some twinkles. What is the name? Something like that. Extrusion, right? And then injection molding. Okay, and then 6.4.3. That's compression molding. And then also transfer. (6.2) that's casting. Casting, not much we can talk. We just cast, And then 6.4.6. So this is point 6. That's thermoforming. Forming. Okay, so we want to cover these, kind of, transfer molding. Yes, I think these process, but somehow I want to mention the important things. So this, injection molding or even extrusion, that's going to be like large quantity, right? Because otherwise you cannot pay for the machine. You have to make a lot. So this probably thermoplastic and thermoset. You can, but somehow maybe thermoplastic. So that's or thermoplastics. That's probably more suitable. You can still It's not like you cannot, but So maybe the parenthesis, right? Then compression molding, So then thermosets, how they are made, how they can be used. So the compression molding. So that's actually a lot, most of the case, because it's not flowable. So you put a little bit and then warm up and then compression. Again, I will share the video and the picture soon. So this, and then also transfer molding, thermosets, maybe used more. So this, I will leave, figure. This one, figure 6.15. This is figure 6.16. And cast I've already made. Casting is casting. So okay. I think that then before we watch video. So thermoforming. Thermoforming is the one to make like a plastic cup, like transparency cup. You pour a drink. She's drinking coffee. That's sorry, yeah, that's one. Right? That's thank you for volunteering. Right? That's thermoforming. Because how much you are going to cost? Usually, it's like a stack, right? And then if you go to store, you can buy like maybe 30 or 50, and then you can buy certain, kind of cost, right? And then you are using only probably one time. So basically, starting from the film, and then films, or sheet, and then you warm up, and then you have mold, and then like warm up, and also you vacuum, and then adhere. Well, no, I shouldn't say adhere. Just like maybe replicate, or just cover to the mold, and then you remove it, and then you can go mass production. Okay, so this thermoforming is key is a film or a sheet. Oh. Okay, so film or sheet of or but this one thermoplastic. Okay, so basically heated above transition temperature, and then like little bit soften, right? Sorry, a little bit thermoplastic, so soften, and then let it cool down. Okay, this is thermoplastic. Think that's so this you need like a mold, right? And then usually they use vacuum mold, but they have vacuum. I think I'm using one too much. Vacuum. This is too much. Vacuum. I cannot write vacuum. Oh my goodness. U too, 2U. I don't know how many. Professor don't know how to write vacuum. I'm in trouble. But anyway, this is the vacuum. And then other than that, there is no figure 6.44. 6.44. We need to think. This is not like thermoforming, but I will explain when it comes to thermoforming section. Okay? And then I think 6.44 and 6.14A. Okay, that's we want to talk about when time comes. When time comes means when come to picture. So okay, can we move on to like picture or video or something to explain more? So let's go back to first extrusion. So extrusion is just similar to injection molding. So because you extrude, so then we have video. So let's watch video first. So this is forming process, and then already plastic. This is plastic processes. So then we are going to start from this injection molding, and we want to also watch blow molding too together, or continuous, let's say.
To better understand the injection molding process requires understanding some properties inherent in plastic itself. The simplest definition of a plastic is any natural or synthetic polymer that has a high molecular weight. There are two types of plastics, thermoplastic and thermosets. Thermoplastics undergo a reversible change from solid to liquid when heated, and can be cooled and reground for reuse over and over again. Thermosets undergo a chemical reaction between two reagents when heated and achieve their strength through the interlocking chemical bonds. Once molded, thermosets cannot be resoftened. While thermosets are injection moldable, most materials used in injection molding machines are thermoplastics. Injection molding plastics is extremely complicated because of the infinitely changing pressure, temperature, and velocity inside the mold. These molding conditions directly affect the properties of each molded part. A change in any of the conditions will alter the parts produced. There are 4 primary elements that influence the plastic injection molding process: the molder, the material, the injection machine, and the mold. There are a variety of injection molding machines in use today. The vast majority of these machines are hydraulically actuated and have 3 platens. But newer styles, such as 2-platen injection molding machines and electric injection molding machines, are now gaining market acceptance. Injection molding machines range in size and complexity from desk-size units up to machines the size of a small house. Most injection molding machines are horizontally oriented, but vertically oriented molding machines are available. These vertical machines are primarily used for insert molding. All injection molding machines are a combination of 2 systems: an injection system and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are 2 types of injection mechanisms: the reciprocating screw, which is the most common, and the 2-stage screw. The main parts of the reciprocating screw injection system are the hopper, a reciprocating screw inside an externally heated injection barrel, a hydraulic motor, and an injection cylinder. Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum-fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle. Over time, many different mold designs have been developed that meet specific injection molding requirements. These mold designs include the Cold Runner 2-plate mold, the Cold Runner 3-plate mold, the Hot Runner mold, and the Insulated Runner mold. The Cold Runner 2-plate mold consists of 2 plates with the mold cavity and core mounted on them. The Cold Runner system molds the sprue, runners, and gate along with the parts. After ejection, the parts are separated and the rest reground. The Cold Runner 3-plate mold uses 3 plates to mold the part. These plates include the stripper plate, which contains the sprue, the middle or cavity plate, which holds the cavity, runner, and gate, and the movable plate, which holds the molded part. This type of Cold Runner mold design automatically separates the runner system from the part as the mold opens and is very easy to automate. The Hot Runner mold uses an electrically heated manifold that keeps the molten thermoplastic in the runners at the same temperature as the heating cylinder. The heated runner system is contained in a plate of its own and does not open during the molding cycle. Because of this, hot runner molds generate no runners or sprues. For this reason, hot runner molding, also known as runnerless molding, is fast and efficient. The insulated runner mold is much like the hot runner mold, but it uses a large diameter runner. During injection, the outer surface of the runner freezes. This insulates the center material, keeping it at the molding temperature.
Okay, so this is injection molding, but it's really kind of, mechanical, right? But same thing before we go, one more, injection molding. So this, oops, I think I put the lecture. Sorry, I have to go. I accidentally closed it, class. You see my, all the system, not this one. I think this, this is the first chapter 4 and 5, but the next page, it's already, uploaded on, September 25th. But I want you to, pay attention this Lego. So I think I touched somehow Lego a little bit, I'm not going to watch all 8 minutes, but I believe at least one time everybody touch Lego, right? Right? Did you see all the Lego product? L-E-G-O, Lego? That's impressive, right? How many millimeters are width? It's not even 1 millimeter, right? You have to flow. The mold is made, because it's always recess or, protrusion. Which one? Do you remember the Lego character?
The Lego brick is 30 and 300. The granulate is fed down a labyrinth of long pipes into the pipes lead to the heart of the Lego factory, the molding area. High-tech injection molding machines produce Lego elements 24 hours a day, 7 days a week. First, the raw granulate is mixed with the dye. Bricks are currently produced in over 50 different colors. The colored granulate is then led into the molding machine. Within no time, the granulate is heated to between 230 and 310 degrees Celsius. The plastic melts into a texture much like toothpaste. With great force, the paste is then fed into the mold. Great forces must be controlled during this process. The pressure can reach 29,000 psi. In comparison, a car's tire pressure is 29 to 43 psi. In the mold, the material is cooled in a matter of seconds, and out comes a newborn Lego brick as we know it.
This is how Lego is made. I'm going to stop. So it's the previous video. It looks really, kind of dark side, right? It's like a metal and dirty machine. But if I same process, but if I show Lego, it's more beautiful, right? But it's the same, principle, So, but anyway, if you still have Lego at home, or when you go home on Thanksgiving or Christmas time, take a look at each Lego characters, like a trademark, right? How precise, and they groove, right? And then you process. So Lego can be like protrusion, right? The character, right? So, and then also color, I might have mentioned, so there are each different colors. Probably when I was young, then maybe limited color. But now, even if it's like red, variety of red through orange, that, kind of transition. And then, if you want to collect or you want to fix some of your Lego, you can contact Lego. Lego is from which country? Where is the headquarters? Denmark, correct, right? And then maybe you don't have to go to Denmark, even I think United States, Texas, somewhere in a factory, Then they can tell exactly what color you want to have and they can give it to you. And it's still really nicely matched. That's amazing, right? Because Lego, additive manufacturing, right? You've been doing additive manufacturing since you are what? 2 years old or 3, like Duplo. Remember Duplo? The big one, right? And so, and then precisely, because even kids' force, how much, like grabbing force kids have, they can do, and then they can remove, right? So that's, kind of very precision. But anyway, this is, injection molding. And then how about, blow molding? I want you to watch when you get home, Then blow molding is the blowing, so I'm not gonna do, balloon or others, I want you to take a look, but let's go back to this, plastic blow molding,
Blow molding processes are the most popular methods used to produce hollow products out of thermoplastic materials. Blow molding evolved from the ancient art of glass blowing. Today, it is a leading plastic manufacturing process. because of the wide range of plastic resins that can be blow molded and the many possible methods of blow molding. Blow molded parts range in size from the very small to extremely large parts. Bottles and containers are the most common blow molded products, but other items such as highway barrels, automotive components, double-walled cases, toys, medical items, and structural panels are produced. Blow molded products are formed from thermoplastic resins such as high-density polyethylene, medium and low-density polyethylene, polyethylene terephthalate, polypropylene, polyvinyl chloride, thermoplastic elastomers, polystyrene, polycarbonate, fluoropolymers, polyimide, and many other materials. Most thermoplastic blow-molded products are produced via extrusion blow molding using high-density polyethylene or HDPE, but there are many additional blow molding processes which include injection blow molding, biaxial stretch blow molding, and co-extrusion blow molding. These blow molding processes all use elements of either extrusion or injection molding or a combination of the two. In addition, these blow molding processes all share 4 common stages: plasticizing or melting the resin, parison production when referring to most blow molding operations, or preform production when referring to biaxial stretch blow molding, parison or preform inflation and cooling in the blow mold, and ejection from the blow mold. A 5th stage is necessary in extrusion blow molding for trimming and finishing the product. For the most part, blow molding processes all use the same blowing technique, whether it be through a blow pin, a needle, a stuffer, or core rod. It is in the production of the parison or the preform where these processes differ. The process of extrusion blow molding involves applying heat and pressure to thermoplastic resin to produce what is called the melt. This melt is then forced through a die to produce a parison, which is then dropped, trapped, or conveyed to an open blow mold for subsequent blow molding. Extrusion blow molding uses either an intermittent or continuous method for the formation of the molten parison. Intermittent extrusion produces a parison only when the blow mold is ready. These parisons are produced by using either a reciprocating screw or an accumulator and ram-style machine. Injection blow molding incorporates elements of conventional thermoplastic injection molding with blow molding and is generally more economical than extrusion blow molding for containers under a 1/4 liter in size and large production runs. Injection blow molding machines typically contain 3 stations: the injection station, the blow station, and the strip or eject station. The injection station is basically an injection molding machine. A ram, usually a reciprocating screw, forces the melted thermoplastic resin under pressure onto a metal core rod held within a closed, split parison cavity injection mold. After the outside skin of the parison has set, the parison mold opens, and the core rod carrying the parison rotates to the blow station. Once the core rod is in position, the blow mold closes. A trigger bar opens the core rod air passage. The air lifts the parison from the core rod except where it is held at the neck and expands it to the shape defined by the blow mold cavity. Once the part has cooled sufficiently, the blow mold opens and the part is indexed to the next station for stripping or ejection.
Okay, I think 140. So maybe next time I will, cover another video or some, picture to complete, and then we will move on to chapter 8, machining section. Okay, thank you.